Hey guys, I guess it's going to be a long day, but final day. So we are going to talk about VxLAN, BGP, EVPN. How many of you are from data center environment or managing data centers using VxLAN? Okay, that's cool. Okay, you might eventually turn into using VxLAN, BGP, EVPN. All right, so what we are going to discuss today is on a few things, giving an overview of how VxLAN works or what VxLAN is, the older models of data forwarding, flood and learn mechanism, Ingress Replication, and then we'll look into the downsides of it and move on to VxLAN, BGP, EVPN to see how it can benefit to scale the data centers using BGP. We'll be seeing different components of it and how the BGP route looks like for in an EVPN environment. So what is VxLAN overlay, or what is VxLAN itself? Traditionally we have been using layer 3 over layer 2, layer 3 IP addresses over layer 2 environments, right? VxLAN is just opposite, using layer 2 overlays on top of your layer 3 underlays. You have IP protocols running at the bottom, different protocols, and based on your IP reachability, you have different endpoints which terminate your circuits or your virtual LANs, and you can do the forwarding and routing between them. The benefit of VxLAN is it has a 24-bit segment ID, which uniquely identifies the segment and can help you scale the network. So you don't have the limitation of 4094 VLANs that you used to have with regular VLANs and spanning tree protocols. But now, and at the same time, you also get the benefit of ECMP paths with underlay IP routing. So this is how your model looks like in your data center. You have your IP network underlay, having reachability, you have OSPF, ISIS, whatever you want to run in your underlay, and you have your local LAN segments. The endpoints, you can also call them VTEPs, virtual tunnel endpoints, which are terminated at the edge devices, where they have the C interfaces or C connected VLANs, or classical VLANs, you may say, and on the other side, it provides IP connectivity to the other remote endpoints. On top of these IP network or IP reachability environments, you have your VxLAN running, wherein you have the connections to the remote ends. All the packet forwarding is encapsulated into VxLAN packets and forwarded across. So your IP packet, before we move on to how the packet format looks, so you have your regular packet from the C device or the end host, which is then encapsulated similar to what you have with GRE in VxLAN packet, and then transmitted over to remote endpoints where it's decapsulated again and forwarded to the other LAN segment where you actually want to send the packet. So, few definitions. What is a VDEP? You have a device which actually works or takes care of encapsulating and decapsulating the regular CE VLAN packets or CE side or end host packets, and convert them into VxLAN forwarding packet itself. You also have VxLAN gateways to bridge or route the traffic based on what from where you're receiving the traffic. So you want to do a bridging between VLAN to VLAN traffic, or bridging from VLAN to VxLAN, or routing between VxLAN to VxLAN based on different scenarios of how your environment is set up. This is how the encapsulation looks like. So you have your regular Ethernet header. On top of that, you will add a VxLAN header and your external IP header where you have the outer Ethernet, outer IP address, and your UDP port. Your UDP port is static for the VxLAN, which is right now at 4789 port number. Your VxLAN header also has the instance ID, reserved bits, and flags. The instance ID is the one where you have most of the fields defined, or your segment IDs or instance IDs defined. The encapsulation, when happens, the second header that you're looking at is where your VxLAN packet will look like in your data center environment. The packet that actually comes in or goes out towards the end host is the top layer packet. Now, you have two gateways, layer 2 gateway and the layer 3 gateway. As I mentioned before, when you have a traffic require layer 2 bridging from VLAN to VxLAN encapsulation, or you have any packet coming in from a tagged interface, .1 queue interface, and going towards a new VLAN in a bridged packet format, that's where you use layer 2 gateways. On the other side, you have layer 3 gateways, which takes care of doing VxLAN to VxLAN routing. So any packet that comes which requires a routed action on it requires the VxLAN layer 3 gateway. Flood and learn. As the name suggests, you actually learn about the remote host and the remote endpoints based on the data forwarding. Unless you have data forwarding between end host to end host, or say for host A tries to reach out to host B, unless that happens, your endpoints will not be talking to each other, or they won't be knowing each other that there's a connection or they require a connection. So you have NV interfaces which don't get established, or NV peers don't get established unless the actual data forwarding happens. You have the BUM traffic. It's a good name, abbreviation, right? Broadcast, unknown unicast, and the multicast traffic, they all are flooded into your data center environment with the default flood and learn mechanism. It's not a good thing, because if you have tens of thousands of hosts in your environment, a lot of flooding will take place. Who wants that in the data center, right? What happens with flood and learn mechanism is you make your segments part of a particular multicast address, and on the remote VTEPs, you also have similar VNIs which are subscribed to that same particular multicast group. And that's how the communication happens. When the packet comes in, based on the subscription, whoever has that subscribed to or joins that particular multicast group, the packet is forwarded to those endpoints, and the encapsulation and decapsulation happens. Let's see how the packet forwarding works in a flood and learn mechanism. So the host, you have three hosts, A, B, and C. They have their separate MACs and IP addresses. You have three virtual VTEPs, VTEP 1, 2, and 3. Again, they have their own MAC addresses and IP addresses. Now what happens is when the packet comes from the host saying, I need to reach to host B, obviously the first packet will send as a broadcast. So the VTEP receives the packet. Since it's received on a classical VLAN, which is now part of the VxLAN segment, VxLAN routing environment, what it does is it sends a flood, or it floods the packet into the VxLAN network itself based on the multicast address defined on that VNI. Now, since there's a multicast group 239.1.1.1 and it's configured on both the VTEPs, VTEP 2 and VTEP 3, both of them receive the packet. Now, when they receive the packet, notice that it's a VxLAN packet. It has the VxLAN ID, which uniquely identifies the segment. Also notice the outer source IP and the destination IP. The destination IP will be the multicast address because it needs to flood to all the subscribers who are subscribing to that particular multicast group. When it floods there, both the tunnel endpoints or VTEPs receive that packet and update their MAC address table, saying MAC A of host A is received as a VxLAN packet, so VxLAN ID 10. And it also gives you the IP of the remote VTEP. So 192.168.1.1, whichever the IP is of the source or ingressing VTEP. Now, since host VTEP 3 does not have the host or the destination host, eventually it'll drop the packet, but then the VTEP 2 has the host B attached to it. It'll forward the packet, and host B responds and saying, okay, I have the MAC. This is my MAC, and this is a response from B. It then again sends the packet back to VTEP 1. Now, when the VTEP 1 receives the packet, it then updates its MAC address table with the VxLAN segment ID and the remote VTEP ID saying who has the MAC address B of host B, which is 192.168.2.2 remote VTEP 2. And once this is done, the response comes back to host A, who is the initiator of the traffic. Now, this is the whole process of learning about the different VTEPs, and you can notice that there's so much of flooding going on within the environment, which is not a scalable thing. Once the VTEPs are learned based on the host addresses, they can then perform unicast forwarding within the network. So this is how flood and learn works. Now, you also have Ingress Replication. In Ingress Replication, not everyone wants to run multicast in the environment, so you have unicast forwarding. And the downside of it is you need to have the packets replicated, unicast packets replicated to all the VTEPs. Unless you do that, not all VTEPs will be able to form a neighborship or NV-peering and be able to establish a connection to forward the VxLAN packets. And specifically on Cisco platforms, there's a recommendation to not use more than 16 Ingress Replication VTEPs. You may face some scalability challenges there. So all in all, both the flood and learn mechanism and the Ingress Replication mechanism are not so scalable. So what do we have? The problem here is you need host mobility. You also need optimal east to west traffic. At the same time, you do not want flooding in your network. How can you prevent that? Here, you come up with the solution of anycast gateways, in fact, distributed anycast gateways, and which can take care of your forwarding or east to west traffic. And the solution to the whole problem is to reduce the flooding and all the problems that you're facing with the regular flood and learn mechanism or Ingress Replication is using the BGP extension, which advertises two routes for each end host. One is the layer 2 MAC address, and one is MAC plus IP information. So whenever the BGP advertisement goes out, it has layer 2 plus layer 3 information. You also have VxLAN overlay, distributed anycast gateways, and ARP suppression. We'll discuss about the benefits of ARP suppression, because if you have bump traffic in your network, ARP suppression can actually help you with reducing the flood in the network within your data center environment, not towards the classical CE interfaces, but actually towards the VxLAN or the layer 3 network. Now, why control plane? We have it for years. BGP has been running for years and years, and it's the more scalable protocol. So even if you have tens and thousands of hosts, it's still scalable, and you can just use another address family to get that working. And with now, you have EVPN address families, which can be used to advertise those VxLAN or the VxLAN host information. It also has, it also carries both the layer 2 as well as layer 3 reachability information. So you don't have to worry about advertising just layer 2 or layer 3. When a host reaches out or sends a gracious ARP, it updates all the remote VTEPs who are part of that tenant. So what are the different components? When you have a EVPN scenario, you have a tenant. Usually, you can correlate as an MPLS VPN deployment with VRFs, virtual routing forwarding instances. And in that VRF, you have multiple layer 2 VNIs and one layer 3 VNI. Now, the layer 2 VNIs take care of doing all the layer 2 forwarding stuff or the bridging of packets, whereas the layer 3 VNI takes care of any routed or takes care of treating or processing the routed packets, you can say. So this is how your regular deployment will look like. You have IP multicast core, you will have spine and leaves, and on the leaves you will have the endpoints terminated. You will have different leaves part of a particular tenant. In the tenant you will have both layer 2 and layer 3 VNIs. So remember, there will be only one layer 3 VNI, and you can have multiple layer 2 VNIs per tenant. So Over here, if you can see, you have different layer 2 VNIs and one layer 3 VNI. When the host advertises the addresses or sends an ARP, the BGP EVPN comes into play to advertise both the information, that is MAC and MAC plus IP information to the remote endpoints. And this is how the learning works. You don't have to actually have a real data from host A to host B to actually have the learning of the remote endpoints. And this is how actually VxLAN BGP EVPN provides peer auto discovery. So again, it minimizes the flooding in the network. It provides or optimizes the east to west and north-south traffic. North-south means your up to down traffic. You have peer discovery, and you can use all the benefits of BGP protocol itself. Now, I was talking about the distributed anycast gateways. What it does is you actually have hosts of same subnets maybe residing on different VTEPs. And it becomes hard to communicate, or you have a single gateway residing somewhere on the remote VTEP. What you do is, with distributed anycast gateway, you have an anycast address, which is configured with the same IP address on all the VTEP endpoints. This actually helps with maintaining east to west traffic in a seamless manner, so that if you want to verify the reachability of a particular host, or if a host is not working, instead of unconfiguring the interface and configuring an IP address to see if the host is working or not, you can actually use this anycast gateway IP to ping the host and see if the host is reachable or not on the VTEP itself, rather than doing the traditional way of troubleshooting for host reachability. This is a sample configuration on how you can configure it on Cisco platforms. Honestly, I'm not well aware of other vendor platforms, so couldn't provide the configuration for that. But I'm pretty sure it should be available for them as well. ARP suppression. Now, what happens is you want to get rid of unnecessary or unwanted flooding in the network. ARP suppression does that. When a host comes up, it sends a gracious ARP request. At that point, the VTEP updates the remote endpoint. At the same time, it also updates the ARP suppression cache. With that, what happens is, instead of, if host B tries to reach out to host A, instead of flooding those packets, it will look up for that MAC address, who holds that MAC address, into its ARP suppression cache, and do the forwarding directly to that particular endpoint, rather than using multicast packets to flood it in the network. This saves a lot of flooding. So the ARP suppression cache, obviously you have to, specifically on Cisco platforms, you have to carve out the space to maintain that cache on the local VTEPs. You have different forwarding mechanisms on with VxLAN EVPN. You have asymmetric and symmetrical ingress integrated route bridge modes. With asymmetric, what you have is this, the packet forwarding path is different than the return path. So if a packet has to reach from node VTEP A to VTEP B, it might take a different path on their way back when the response comes back. With symmetrical, it's same path. So VNI A, which is a layer 2 VNI, communicates with layer 3 VNI of the same tenant on same VTEP, and then forwards the packet to the remote VTEP on the layer 3 VNI. The layer 3 VNI then communicates to the local layer 2 VNI where the actual packet resides, and forwards the packet to the host. And on the reverse, again, the same process. So it uses the same path back and forward for the symmetrical IRB. The Cisco platforms support symmetrical, they do not support asymmetrical IRBs. Now, with BGP EVPN, you have different kinds of routes available with you. You have type 1, 2, 3, 4, 5, but most importantly, you need to worry about, or while troubleshooting and understanding the packet flow, you need to take care about the type 2 and the type 5 routes. Now, type 2 has the MAC advertisement. You have the MAC and the MAC plus IP information, which is advertised as a type 2 route. And you have the IP prefixes, which are advertised as type 5 routes in BGP EVPN. We'll go through how those prefixes look in the coming slides. The type 3 is usually used with your Ingress Replication. So you can use Ingress Replication again with EVPN as well. So you can, in your core, still have multicast. You will still need multicast or Ingress Replication method along with running BGP EVPN. But it's just that BGP takes care or reduces the overload in the network by reducing the flooding and just takes care using BGP updates. Now, how does the BGP prefix look like? If you have a MAC address of a particular host, you can look into the BGP table saying, show BGP L2 VPN EVPN, or maybe a different command line based on the vendor you're using, and you can look for that MAC address. If you look at the MAC address, you can notice a pretty long prefix. The first section, the first highlighted in purple is the route type, which is 2. Then you have the Ethernet segment ID, Ethernet tag ID, the MAC address length, which is 48. Then it shows the MAC address. Remember, this is a layer 2 VNI, so it will only have layer 2 information, MAC address, not MAC plus IP. So you have the MAC address. You can see the IP address length and IP address field itself is set to 0.0.0.0 because there's no IP information shared as part of the layer 2 VNI. And then you have also have the receive label, which is the segment ID, the layer 2 VNI segment ID, which is assigned to that particular VLAN segment. This is then advertised to the remote VTEPs. This is on the local side, but this gets advertised to the remote VTEPs whenever there's a gracious ARP. And similarly, the layer 3 VNI information also gets advertised. Now, how does the layer 3 VNI information looks like? You have a prefix 100.1.1.1, which is assigned to a particular host, end host of the VTEP. And you look at on the remote side, you will notice first, you will notice you have the route distinguisher, layer 3 VNI, similar field, but now you also have the IP address length and IP address populated in that prefix itself. And obviously, the size of the prefix will increase because of the information carried. At the bottom, you're not just seeing one label. Now you're seeing 2 labels. Now these 2 labels are one for the layer 2 VNI, and other one is for the layer 3 VNI. So if you look at the EVPN route fields, you will notice that you have options for label 1, which is L2 VNI, and label 2, which is the layer 3 VNI. This is how the information is exchanged over EVPN, and you can perform VxLAN routing using BGP. That's it. If you are looking for any troubleshooting documentation on how you configure VxLAN EVPN, this book is coming out in December. You can refer to that on Cisco platforms. Feel free to buy it. The more you buy, I'll get to buy more beers and be crazy to write some more content. All right, questions?
John O'Brien, University of Pennsylvania. Could you please comment briefly on MTU requirements for VxLAN and how exceptions are handled?
Oh, right. So usually your end host, in normal deployments, you will see that your end hosts are running with the default MTU of 1500. So in your core, you can actually add the additional bytes of VxLAN headers and other outer IP headers to take care of the forwarding. But nowadays, what happens is usually they configure 9100 or 9216 MTU size in the core network, which takes care of all the MTU issues that could possibly happen.
And what about exception handling? If those requirements aren't met, is there a way that the VTEPs handle that?
So there are different command lines available on platform-to-platform or vendor-to-vendor basis, which you can actually use to understand, okay, this is the cause of the packet forwarding not happening. Maybe an MTU issue or maybe a reachability issue. Different things. So there are command lines available.
But it doesn't sound like there's any signaling on the network on the wire.
I don't think so.
Thank you.
Any other question? Cool. All right. Thank you, guys.